So those examples right there had the natural log in it or had logarithms in it. But what if it's really messy, like these are super messy as well? This one is super, you have multiplication, you have division, you're going to use quotient rule, you're going to use the product rule, you're going to have to use power rule, you might even have to use chain rule. There's a lot of functions going on. So we could kind of cheat the system a little bit and use what we know about logarithms to help us. So what we're going to do is we're going to take the natural log of both sides of this equation and then work from there. Because then I can expand. I'm going to write this as x plus 1 to the 1/3, like that. And then I have the natural log of y is equal to, expanding is going to give me the natural log of x plus 3/2 natural log of x minus 1. And then the denominator is going to be a minus 1/3 natural log of x plus 1. And then I'm going to take the derivative with respect to x on both sides. So I'm going to do d dx on the left-hand side and d dx on the right-hand side. Natural log of x plus 3/2 natural log of x minus 1 minus 1/3 natural log of x plus 1. On the left-hand side, the derivative of natural log is 1 over u, or in this case it's y, 1 over y. But using the chain rule, you have to take the derivative of y with respect to x. That's the inner function. So that's going to be dy dx is equal to, and then 1 over x plus 3/2 times in the denominator x minus 1 times the derivative of x minus 1 is just 1, so I don't need that. 1/3 in the denominator times x plus 1 times the derivative of x plus 1 is just 1, so I don't have to write anything there. So far I have dy dx, and then over here I have 1 over y, but to get rid of the 1 over y, I'm just going to multiply both sides by y. So that's going to give me 1 over y times 1 over x plus, and you know what we could do while we're doing it? Well, no, you know what? I'm going to leave it here for 1 over x plus 3/2 x minus 1 minus 1/3 times x plus 1, like that. And then I want everything in, most likely in terms of y, so I'm just going to switch colors. Y is defined up here, so I'm going to rewrite y in here. It's going to be x times x minus 1 to the 3/2 over x plus 1 to the 1/2. And then inside of this parenthesis, I could actually start simplifying. So I need a common denominator, which would be 6x, x minus 1, and x plus 1. And then the first one is missing the 6x squared minus 1 plus 3. I'm just using I'm using this and multiplying those together to get what I need to multiply up here by. And then 3 times, I'm missing an x, a 3, and an x plus 1, and minus 1 times, I'm missing a 2, an x, and an x minus 1, like that. Alrighty, so a couple things that I notice. For example, this and this will cancel each other out. Well, that's convenient. Okay, so let's get rid of those. I also notice that this one here and this one here have the same base. So I can combine them into one spot. In this case, the numerator has the higher exponent. So I'm just going to subtract the exponents and get x minus 1 to the 1/2 in the numerator. And also this one and this one have the same base. I can combine and get a single numerator for those. So let's look what we get. So we are at dy dx is equal to x minus 1 to the 1/2 because I'm combining those two. And I'm getting 6 is still there, but the blue ones that I highlighted is going to give me x plus 1 to the 3/2. I'm just adding the exponents. And then I'm going to simplify all of this stuff here. So in the numerator. So let's, the one I'm highlighting in yellow right now, all of that mess, I'm going to have to simplify. But what I'm going to do is I'm going to simplify it on the side over here and then get rid of, or maybe underneath here, just as scrap paper. So 6x squared minus 6 plus, that's 9x, 9x squared, 9x, so that's 9x minus, that was a 2 there, that's really hard to see, and a times. So negative 2x squared, and then negative becomes a positive plus 2x. So combining all of the like terms from that, I have all of the x squared terms is going to give me a 13x squared, and the x terms is going to be plus 11x and a minus 6 in the end, like that. And then I think that does it. There you go. Now pause the video. I'm going to erase down here. I don't need that. Pause the video and do part B. Done the similar way. Take the natural log of both sides. And that's what I'm getting for part B. When should you use logarithms to help you differentiate? When you have lots and lots of different operations happening, like if you have to use the product rule with the quotient rule, with the, then it's much easier to use the natural log of both sides. So when multiple rules like product and quotient rules are needed. Why is it helpful? Well, because it's much easier to take the derivative of a natural log, and I get it's a little messy at the end, but the algebraic messiness of this is much easier than having to do it the other way. Okay, so example 10. I am aware that the previous example, the restriction is missing in the video, but it is in your notes. And I used to have that example in a different spot in my notes, and I changed my mind. So I'm moving it to here. But the questions are the same, and the process is the same in the previous video. And I also moved the question, what should we use logarithmics to help differentiate? So just to clarify that example 9 is the previous example. I just, part B, for some reason, that one didn't have the restrictions. But just know that the restriction belongs there. Okay, for this particular question, we are going to let, when you have a base that is a variable and you have the exponent that's a variable, it's kind of a unique situation because I can't use the power rule because the exponent is also a variable, and I can't use the exponential rule because the base is a variable. So the only way we can address this is really take the natural log of both sides. That's the safest way to do this. So x to the 4x, I'm going to use properties of logarithms by moving the 4x out in front times the natural log of x. Then I'm going to differentiate with respect to x on both sides implicitly. So I'm basically doing this problem implicitly. And then remember, on the left-hand side, the derivative of the natural log of something is 1 over y. Using the chain rule, the inner function is y. So that's going to, the derivative of y with respect to x is dy dx. And then is equal to, and here I have to remember to use the product rule. There's two functions. There's the 4x and there's the natural log of x. So we end up getting the first, which is 4x, times the derivative of the second, which is 1 over x, times dx over dx essentially here. It's dx over dx is equal to 1, so we don't need to write that, plus the derivative of the first, which is 4 times dx over dx, which I don't need to write here, it's just 1, times the natural log of x. So let's simplify a little bit. So in our particular case, we get 1 over y times dy dx is equal to, now the x's cancel out, so essentially I get 4 plus 4 times the natural log of x. And then to solve for dy dx, I'm going to multiply both sides by y. So 4 plus 4 natural log of x. And then, y was equal to x to the 4x. So dy dx is equal to x to the 4x, and then 4 plus 4 times the natural log of x. Now, the preferred form is factored, so I could take out a 4. I mean, you're kind of done here already, but if you took out the 4, that would be nice. 1 plus natural log of x. Both are acceptable. I'm just pointing out that you could do this. And the same again, x has to be greater than or equal to 0 because the base has to be a non-negative. For part B here, we also need a restriction, and it is x has to be greater than or equal to 1. No, greater than, not equal to. It doesn't make any sense. So here, greater than 1 in this case, so that we don't get a base that's negative. All right, now try B on your own. Pause the video, give it a shot, and then see if you get the right answer. Okay, this is what I got. Okie dokie. So then, even though we answered it in the previous video, when should we use logarithmics for differentiation? One is if you have a lot of, a mixture of a lot of operations. And another case, which is this case here, when you have a variable raised to another variable. So like a power that is a variable, but the base is also a variable. Those are the cases, which makes the problem a lot simpler than trying to suss it out any other way.